neighborhood. I'll say hi.
All right, all right.
This is such a truth.
Have a good weekend, guys.
Thanks, you too.
Yep.
What version are you running for Nodal?
It should be just whatever's here. I think it's 2021, I want to say. Or 2019. Oh, wait. 2021. Yeah. 2021A. Are you guys running into some issues? Okay, let me prep for the next class, then I'll come check on you guys.
Say horse. Oh, you run? Yeah. I like, my sister runs. She's yeah, she just got her first. She plays. Yeah. Like, I think she's from outside, so. You like go off where she like teach lessons and then pay her. They checked them out, saying they tied her for 6 months and then where she is. Yeah. Other than my dog and pet, like as far as you got it? Yeah. Okay.
Okay, so right now it said your matrix is singular. So let's look at your left hand side. Oh, okay, so it looks like you have some type of I see.
Oh, I see.
And so let's come up.
Yeah.
So when you first find your left, so there's a type of representation left hand side matrix. Okay. And then, so make sure all of these are all these are yeah, just there's okay, I think there's still some type of I'll go ahead and close this. Okay, so you can see here there's one. Oh, just make sure.
Yeah, that's I was surprised when the other one. That's like that hurts me. Well, we used to sign in for like other users. Oh, yeah, that's how I don't know. You're right.
me a favor, let me go ahead and let's comment out the bottom. So remember, I started out with code 3, but let's go ahead and comment those 2 lines out. Come down. Comment out these 2 lines.
Pretty much just like doing my favorite better.
Yeah, no problem. You guys. Grab that right here. Okay, so let's double click this. Let's see what this looks like. It looks like the 4th row wasn't assigned, so let's go back to the 4th row.
No, it's not the time I know. Most of those people are the best. Proofs of gravity.
Yeah. So you have 2nd equation, 3rd equation. Come down.
Yeah.
So you don't have the code for the 4th row. So there should be one
Yeah, that's
more
true.
code one.
So it's like, I've been doing it for like 6 or 7 years now. So
So if you need to do it, so this is for the right hand side, that's, you need to do it for the left hand side. Because you're only, because right now because you need to assign both the coefficients of the left hand side matrix and in the right hand side. And so you need to keep this as whole. But then you need to change, so you need to change this to 4th row, so instead of 3, you're all 4 rows.
Basically, a bunch of different ones with technology, you can just screw in and out.
There's 5 rows, but you don't. So instead of, and then these need to be 3, 4, 5.
And then if anything breaks, you'll-
And then,
Yeah. And it keeps my followers.
okay. Yeah, next time, because it's hard for me to do this a lot, so because I have time to ask this, so next time. Use.
Hey, Dr. Chen, Kamal said he's gonna be late because there was an accident on the freeway.
Oh, okay, no problem.
I'm sure he thought about it. He did. Yeah. You want to- She liked to drive a lot. I don't know if that's the one. She's not like that.
All right, it's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone feeling today? Good, good, good to hear it. All right, so the plan for today is we're going to go ahead and continue our set of lecture notes on truss equations. Okay, and today we're going to venture into the realm of 2D, and so we're going to be doing a lot of trigonometry and a lot of tedious calculations. I'll be the first to tell you that this part of the class gets pretty tedious. I'm not going to lie, but it is good to know. Okay. Announcement I want to make is I posted up the next homework, and so this one is purely just a problem set, and so there's no answers part to this assignment. Okay. And so I think I'm giving you guys about 2 weeks to do it, which is longer than your first assignment. And the reason is because this homework it's a doozy, and so it's going to take you quite a bit of time to do. So I would definitely start it much sooner rather than later, because even if you know kind of exactly what you're doing, just the process of kind of writing everything down and doing all the calculations can still take quite a while. And so I would definitely get started on it sooner. Okay. And a lot of it's going to be based on the direct stiffness stuff that we've been doing. So the spring stuff, the truss stuff, all of that's going to be on the okay. And so I think that's all the announcements I have. And so are there any questions I can answer before we get started? Okay. All right, so let's go ahead and pick up where we left off. So I think we left off kind of right at the end of an example. Okay. And so I think we're working on an example that looks like the following. Okay. And so the example that we were working on was basically we had a series of truss bars. So we have node 1, 2, 3, 4. Okay. We were applying a force of 3,000 pounds on this node right here. Okay. And the length of each element was 30 inches. Okay. And let's see. So the Young's modulus for every element here was 30 times 10 to the 6 psi. Okay. And the cross-sectional area was 1 inch square. Oh, sorry. So this is for elements A and B. Okay. And then element C had slightly different properties. So for element C, we had 15 times 10 to the 6 psi for the Young's modulus, and the area was 4 square inch. Okay. All right, and so what we did for this problem was we walked through our usual finite element process. So we did element stiffness matrix, right? Then we did assembly. Then we did boundary conditions. Okay. Then we solved. Okay. All right. And so, we were just at that point where we could find our solution. And so when we solved this equation, what we got was the displacements at each of the nodes. Okay. And so what we got was U1 was equal to 0 inches. Okay. U2 is equal to 0.0018 inches. Okay. U3 was equal to 0.0006 inches. Okay. And U4 was equal to 0 inches because we had a fixed boundary condition there as well. Okay. Okay. And so I think that's kind of where we left off last time. So are there any questions on any of this? Okay. Okay. And so you would think that once we kind of reach this point, we're kind of done with we're done with the problem. And so we accomplished what we set out to do, was we use finite elements to compute the displacements at all the nodes. Okay. But now that we actually have this solution, we can actually use it to compute some other interesting quantities within this system. Okay. And this is very normal in finite elements as well. And so, even when you're using ANSYS, ANSYS goes beyond just the primary solution variables. And so it doesn't just compute the displacements. And so a lot of times, when we're doing finite elements, we're interested in things like what are the stresses, what are the strains in this system. Okay. And the way that finite elements compute these is they do it based off the primary solution. And so first thing that finite elements does is you compute what's called your primary solution, which is this here. And then that primary solution is used to compute other quantities. Okay. Yep.
Is the displacement always the primary solution?
For structural finite elements, displacement is always the primary solution. But later on, in the second half of the class, we'll be working more with the heat equation. And so the primary solution for that one is temperature, actually. Yeah. All right. And so in this class, or in this lecture, actually, I'll show you a couple of different things that you can compute. But first thing I want to show you is how to compute the reaction forces. Okay. Okay. All right. So if I can draw this figure again. Okay. And so in order to keep this the system in static equilibrium, right? So remember, we're forcing it with a force of 3,000 pounds this way. Okay. In order to keep this entire system at static equilibrium, there has to be some reaction forces that are being applied at the constraints. Okay. And so you can actually use this, the finite element solution, to compute what those reaction forces are. Okay. Okay. And the way we do that is by taking our finite element solution and plugging it back into our global system. Okay, our global stiffness system. Okay. But you have to plug it into the system before you apply the boundary conditions. Okay. Okay. Right. And so in other words, if we kind of follow along our finite element recipe like this, right after this step right here, right after assembly, before you applied the boundary conditions, you had a global stiffness system that was symmetric, right? It's only when you apply the boundary conditions does that system become unsymmetric and solvable, okay? And so if you, once you know your solution, you plug it back into that equation or plug it back into that system, and that'll give you all the reaction forces. And so for this particular problem, we had a global system that looked like this. Yes, we had 10 to the 6 minus 10 to the 6. We had 0, 0, okay? Minus 10 to the 6. 2 times 10 to the 6 minus 10 to the 6, 0, 0 minus 10 to the 6, 3 times 10 to the 6 minus 2 times 10 to the 6, okay? 0, 0 minus 2 times 10 to the 6 and 2 times 10 to the 6, okay? And so remember, this is right after we did assembly. So right after we plugged in all the element stiffness matrices into our system and before we applied boundary conditions, okay? Okay. And so with this system right here, we can just simply perform the matrix vector multiplication because now we know what U1, U2, U3, and U4 are, right? And so all we have to do is just plug it in here. Okay. So now, okay, now these are known. And all we have to do is just perform, the matrix vector multiplication, which usually is a lot easier than solving a linear system of equations. Okay. And what you're solving for now are the various f values, okay? All right, and so if you plug that in for this particular example, what you get is F1 is equal to minus 1,800 pounds, okay? F2 is equal to 3,000 pounds, okay? F3 is actually going to equal 0, and F4, this is minus 1,200 pounds, okay? All right. And so in particular, I want to draw your attention to F1 and F4, right? Because remember, these are where the fixed supports were, okay? And so this F1 and F4, these are forces that the constraints or the supports are applying on the structure to keep it in static equilibrium, okay? And so if you add them up, right, so you add up minus 1,800 minus 1,200, it has the exact same value or exact same, magnitude as the load that you're applying, okay? And the load is 3,000 pounds. Okay? And so you get a reaction force of 3,000 pounds on node 2. That's only because that's where the load is being applied. And so it makes sense that you get, the exact same load there. Okay. All right, and so that's one way that you can use the finite element solution to compute some derived quantities. Okay. And so we'll see some other examples later on, or we'll see one other application later on, where we can use the displacements to actually compute stresses in our truss bars. Okay. All right, any questions on this? Okay. All right, and so that's it for one-dimensional problem. So now let's move on to 2D. Okay. Okay. And so far, we've only just been working on one-dimensional problems, right? And so the displacements are only in one dimension, and all of the springs and all the trusses are aligned, parallel to each other. Okay. This is a fine starting point, and so there are some problems you can do with that. But you can imagine that since we live in a three-dimensional world, if we're limited to just 1D problems, that limits us a lot in terms of what we can do practically, right? And so of course the ultimate goal is to get to 3D, but 3D gets a little bit complex, and so we kind of compromise. And so now we're going to work on 2D problems. Okay. Because I think this jump from one dimension to two dimension, I think, highlights a lot of the steps that you would need to take in order to add extra dimensions to your problem. So I think for this class, just going to 2D is enough. And in fact, once you start doing some problems, you will say that 2D is too much, but we'll get there. Okay. And so the main difficulty that we face when making a jump from 1D to 2D is actually in formulating the element stiffness matrices. Okay. And so when we derived our expressions for the element stiffness matrices, we assumed that the x-axis aligned with the long axis of our element. Okay. Okay. Right. So in other words, we had our truss like this. Okay. And of course, we're going to pull on this with a tension T. Okay. One assumption that we made was that, if we draw our coordinate axes on here, okay, that they align like that. Okay. And so our element stiffness matrix, in other words, was only valid when our coordinate axes kind of lined up just like that. Okay. And so if we were to rotate this, element, okay, if we were to rotate it like this, okay, and if we wanted to use the exact same element stiffness matrix, then that would assume basically that the element stiffness matrix would, excuse me, the coordinate axes would rotate along with it. Okay. Okay. Which, if you're only dealing with one element, that's fine, right? And so if we're only dealing with one element, we say, go ahead and rotate. That's all good. Okay. But most of the time, we're not dealing with just one element. And in fact, most elements in a 2D structure are going to be rotated in arbitrary ways. Okay. And so if we took an arbitrary structure, okay, I'm just going to make a triangle for now. Okay. Right. And if we were to draw an element stiffness or a coordinate axis that's local to each one, okay, it would become kind of a madhouse because we'd have so many different coordinate axes for for all the different elements, and we wouldn't be able to compare, or we wouldn't be able to combine or assemble element stiffness matrices that were formed in different coordinate systems. Okay. Okay. And so this is the main difficulty with working in 2D. And so in 2D, we have to do a bunch of what's called coordinate transformations in order to get basically everything under the same coordinate system. Okay. All right. Any questions on this so far? Okay. All right. And so let me go ahead and define a couple different coordinate systems that we can work with in terms of for these types of problems. Okay. All right. And so first thing I'm going to define here is what's called the local coordinate system. And so the local coordinate system represents the coordinate system of a specific element. So these are ones that kind of rotate along with the element. Okay. Okay. And so using this example that we have up here, right? And so we have our tilted element and the coordinate system that goes along with it, this is basically the local coordinate system. Okay. And usually we denote the local coordinates using a hat. Okay. Right. And so to basically differentiate it from the other coordinate system, we give them little hats. Okay. And so this is usually like X hat and Y hat. Okay. And so that's one coordinate system, right? And so we need that one because that's the only place where we know how to form the element stiffness matrix. Okay. All right. So in addition to the local coordinate system, we need the stationary coordinates. Okay. And so sometimes you'll see these called the global coordinates, but we already use global in our assembly process, and so I don't want to mix up the terminology, and so I'll call these the stationary coordinates. Okay, and these are coordinate axes that do not change at all, and so they kind of stay fixed. Okay. Okay. Right. And so this would be kind of like the classical XY, and so where X is purely horizontal and Y is vertical. Okay. Okay. And so these are the two coordinate systems that we're going to be working with. Okay. And kind of the way that we're going to go with this and the way that we're going to proceed is that the first thing we're going to do is we're going to use the local coordinates to get kind of a first expression for the element stiffness matrix. Okay. Because that's how we we define the physics. Okay? Then what we're going to do is we're going to take that local element stiffness matrix and transform it into the stationary system using coordinate transformations. Okay. Right. And then once we have the element stiffness matrix in the stationary coordinates, then we can directly compare that to, you know, other element stiffness matrices in the stationary coordinates. Okay. And so basically this transformation is what makes assembly possible. Right? Because without this transformation, and we try to assemble element stiffness matrices in all their local coordinates, nothing would match up, and you would get results that make absolutely no sense at all. Okay. Okay. Any questions on this? Okay. All right. And so to kind of give you a visual cue of you know how this is going to work. Okay. Let me go ahead and draw coordinate axis here. Okay, so this would be like the stationary coordinates. Okay. And then over here, I'm going to draw a local coordinate system. Okay. Where the local coordinate system we're going to assume is rotated by an amount alpha, or excuse me, theta. Okay. And so to get from the stationary coordinate system to the local one, we just simply rotate counterclockwise by an amount theta. Okay. All right, and let's consider a certain vector. Okay. Okay. All right, so we'll consider a vector u. Okay. What I hope to do, although my art skills are lacking, is to show you that this vector u is exactly the same. You know, it should be the exact same vector in both coordinate systems. Okay. Okay. The only difference is how we mathematically express its components. Okay. Okay. Right. And so when I talk about transforming, you know, between different coordinate systems, you know, the object itself is staying the same, right? It's like if you're looking at an object, right? So you look at an object from one angle, if you walk over here, you look at it from another angle, it's still the same object, right? You're just looking at it from a different angle. And so, you know, that's the idea with transformations, that you have the underlying object, the underlying physics is still the same. It's just you're kind of looking at it from different angles just to make it convenient to interact with other stuff. Okay. All right, so mathematically, you know, it would look something like this. And so, you know, in the stationary coordinates, you know, we might have something like ux and uy, okay? And I'm going to use kind of the unit vector notation for this, okay? And so this is the components in the stationary coordinates. Okay. And let me not use hats because that's confusing. So let me use I dot and j dot, okay? Where I dot and j dot, they're basically unit vectors in the x and y directions, okay? Right, and so this is going to be equal to the exact same vector, but in the local coordinates, okay? So this would be ux hat, I hat, plus uy hat, j hat, okay? Okay, so where I hat, it looks like this, and j hat looks like that. Okay, so those are simply just unit vectors in the x and y directions. Okay. Okay. And so the key to this expression here is the fact that, you know, these two are the same, right? They're equal. It's the same vector, right? The only thing that's different is the components. Okay. And so the key to our transformation here is to find out the relationship between these components. Okay? Okay. All right. Any questions on this? Okay. All right. So let's start to form those relationships. Okay. And so first thing I want to do is I want to take the I vector. Okay. Let's express the I vector in terms of the local coordinate system, local coordinates. Okay. And so for that, we have an I vector like this. Okay. So this is the I vector. So this is simply just the unit vector in the stationary x direction. Okay. But we're going to break this up into components of the local coordinates. Okay. And so to do that, we're going to make this kind of triangle. Okay. So this is a right angle. Okay. This is an angle theta right here. Okay. And so that's the same angle in which we're rotating with in order to get to the local coordinates. Okay. And the two sides of the triangle, I'm going to call it A hat and B hat. Okay. Okay. And so A hat here, this is the component of I in the J hat direction, or excuse me, in the I hat direction. Okay. Right. Because remember, I hat goes kind of diagonally upwards, just like that. Okay. And we can use some geometry here to find out what that is. Okay. And so the magnitude of A hat is simply going to be I, the magnitude of I, which is the hypotenuse of this triangle, multiplied by cosine of theta. Okay. And then similarly for B hat is the component of I in the J hat direction. Okay. And so the magnitude of B hat is going to be I, magnitude of I sine theta, okay, because it's on the opposite side. Okay, but since we know that I is a unit vector, and so this is just going to be 1, this is going to be 1, okay, and so the length of the hypotenuse of that triangle is 1, okay. We also note here that the B hat vector is pointing in the negative J hat direction, okay. So notice how that B hat vector is pointing down, right? And so, if we go back to our diagram up here, right? The positive J hat direction is kind of pointing up to the left. And since this is pointing down to the right, this is kind of pointing in that negative direction, okay? And so if we combine all this together, then we can say that I, the unit vector in the stationary coordinates, is equal to cosine theta I hat minus sine theta J hat. And so now that we have this expression for I, we can go ahead and plug it back into this expression up here, okay? And we'll do that as soon as we do the same thing for J as well. Okay. All right, any questions on how we got this result here? Yeah, because I is a unit vector, and so I has a magnitude of 1 or length of 1. Yeah. And so basically the length of this hypotenuse is just 1. Yeah. All right, and so that's I. So now let's do the same thing for J. Okay, so now let's express J vector and the local coordinates. All right, and so let's go ahead and draw another triangle here, okay? And so this is J, okay? And so if we draw the components out, this would be like B hat and A hat, okay? But this is a right triangle, and this angle here is theta, okay? All right, and so we're gonna do the same thing as before. So A hat is the component of J in the X hat direction. And so this is gonna be magnitude or J sine theta, okay? Right, because the A hat is on the opposite side of the triangle. So we take the hypotenuse multiplied by sine theta. Right, and the same thing for B hat. So for B hat, we're going to take the magnitude of J and multiply by cosine theta. Okay. And in this case, they're both pointing in the positive direction. So we don't need to adjust any signs. And so we say that J is equal to sine theta I hat plus cosine theta J hat. Okay. All right. And so we got a very similar result here. So we start to get these sines and cosines to come out in these expressions here. Okay. Okay. And so now we have I and J, we can plug it back into our expression above, okay? And so if we do that, we have ux, and that's multiplied by I, and so this can be ux times cosine theta I hat minus sine theta J hat, okay? Plus uy, okay? Uy times sine theta I hat plus cosine theta J hat, okay? And this is equal to ux hat I hat plus uy hat J hat. Okay. Okay. And so what I'm going to do is I'm going to rearrange some of the terms here. And so I'm going to rearrange it in terms of I hat and J hat. Okay. Okay. And so if we do that, we get the following. And so we get ux cosine theta plus uy sine theta, okay, multiplied by I hat plus minus ux sine theta plus uy cosine theta J hat. This is equal to ux hat I hat plus uy hat J hat. Okay. And so what we can do from here is we can turn this into a matrix set of equations. You know, we love to do that in finite elements. And so we see a system and say, how can we put this into a matrix? Okay. And so if we do that, we end up with cosine theta, sine theta, minus sine theta, cosine theta, okay, multiplied by ux, uy is equal to ux hat, uy hat. Okay. Okay. Right. And so this right here is this forms our transformation system, right? And so in other words, you know, that was kind of a lot of trigonometry. But let's kind of pull back and kind of, you know, take a look at what we've derived here. Okay. In other words, you know, what we have here is that if we have a vector, that's defined in the stationary coordinates, Okay. And so in other words, we know its x and y components in the stationary coordinates, right? If we want to find out what the coordinates of that vector is going to be in the local coordinates, or in any coordinate system, that's just a simple rotation. All we have to do is pre-multiply it by this matrix right here, okay? And this matrix is known as the transformation matrix. Well, it's one transformation matrix. And all of math, there's literally a bajillion transformation matrices, but this is going to be our transformation matrix. Right? Because it transforms something from one coordinate system to another. Okay. And the shorthand notation that you'll see me write is instead of writing cos theta, sine theta, cos theta, sine theta, I'll just be lazy and do this. And so I'll do C S minus S C. Okay. And it's going to be equal to our transformation matrix T. Okay. And so when you see me see C, say C, that means cosine theta, and S just stands for sine theta. Okay, so that's just kind of shorthand notation, just to make our lives a little bit easier. Okay. Any questions on this? Okay. All right, and so now that we know what the transformation matrix looks like, let's actually apply this to our truss element. Okay. 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 And so, if you remember, our element stiffness matrix looks like, for a truss, looks like this. Okay. And so we had F1, F2 is equal to AE over L, 1 minus 1 minus 1, 1, U1, U2. Okay. And so that's our element stiffness matrix for a truss. Right? Just to make things consistent with what we've done so far, I'm going to add some hats here. Okay, because remember these are local coordinates, right? Okay. Right, because remember these this element stiffness matrix was defined relative to the coordinate system local to the element. Okay. And I need to do one more thing too, because this element stiffness matrix only assumes that we have displacements in just the x direction. Okay, but now that we're in 2D, we have to account for displacements in the y direction as well, because we're going to have elements that look like this, right? And even though in the local coordinates it's going to maybe displace something like that, right? When we transform this back into the stationary coordinates, these displacements are going to have components in the x and y directions. Okay. Okay. And so we need to expand for that. We need to account for that here. Okay, just because we need to do that for our for our transformation. Okay? And so I'm going to take this and basically augment it with a y component. And so instead of just having F1, F2, I'm going to have F1x hat, F1y hat, F2x hat, F2y hat. Okay. And right now I'm just augmenting it. So I'm not doing any transformations yet. And so, we need AE over L in front. Okay. Okay. And so this is going to be 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And this is going to be multiplied by U1x hat, U1y hat, U2x hat, U2y hat. Okay. Right. And so all I've done is I've just basically taken this and I've augmented it with y components. You'll notice that a lot of it are zeros. because in the local coordinates, we don't have any displacements in the y in the local y direction, right? Because we assume that all of the displacements are limited to just the local x direction. Okay, but we need these y components to be there in order for us to properly apply our transformation. Okay. Okay. Any questions on this so far?
So we're not assuming displacement in the y direction because the local y is lined up straight along the center of gravity of the local
Exactly.
piece of the element or whatever.
Exactly. Yeah. So we're assuming the local y here is basically perpendicular to the element, and so we're not going to get any displacement in that direction, but we will get displacement in the stationary y direction, which is not aligned with the element. But we need to have the local y there just so that we can apply our transformation, basically. Yeah. Okay. All right. And so the next step is that we're going to take both of these vectors, okay, and we're going to transform them using our transformation matrix. Okay. And I'm going to do it in kind of an interesting way because these four vectors are these vectors with four components. They're a little bit unique compared to our original transformation, right? And so our original transformation basically only assumed that we have just an x and y component, right? But not only do we have an x and y component, we also have four different. We have two nodes with x and y components. Okay. And so the exact transformation that we're going to apply actually looks like this. And so I'm going to write the one for. I wrote the one for f actually. So we have f1 x hat, f1 y hat, f2 x hat, f2 y hat. Okay. And the transformation that we're going to apply is we're going to apply basically two, each one in a quadrant. And so we have cosine, sine, minus sine, cosine. Okay. And that's going to be multiplied by f1x with no hat, f1y, f2x, f2y. Okay. And then to transform to the bottom two, we actually need to multiply by the transformation matrix here in the bottom right. Okay, so we have cosine, sine, minus sine, cosine. Okay. And everything else here is going to be zeros. Okay. Right. And so if you actually perform like the matrix vector multiplication on this, you'll see that we actually have our two-dimensional or two vector system here. Okay. And then in order to get the two hats to match up with each other, and so the f2x hat, f2y hat, and f2x, f2y, then the transformation matrix needs to be down here on the bottom. Okay. So this form here is just kind of a result of having two nodes in our system instead of just one. Okay. All right. And so we have this plugin right here, and so we're going to plug in this entire thing in for this right here. Okay. And then similarly, we have another transformation matrix that's going to be applied on the right-hand side of the equation. Okay. And so we're going to replace basically both both hat terms. Okay. It's kind of a lot to write. So let me go ahead and just simplify this. Okay. Yeah. Yeah, it's just to make sure that each node is corresponding to each corresponding stationary one. And so we want the F1 hats and the F1 regulars to be correlated the same. And so that's why we put the transformation matrix in the top left. And then we want the F2 hats to correlate with the F2 regulars. And so we put this one down here. Because if we had something here, so let's say that we had it. Exactly. Yeah. Mm-hmm. Right. So let me do this just to kind of save us a ton of writing, because otherwise it wouldn't fit at all. Okay. So let me call this F hat. I'll call this U hat. Okay. Right. And so our base system, what we have is F hat is equal to K hat, which is our usual element stiffness matrix multiplied by U hat. Okay. Let me call this this 4x4 transformation matrix. I'll call this T with an underline. Okay. Right. And so in our substitution, we're basically saying that F1 hat or F hat is equal to T underline multiplied by F. Okay. And then U hat is going to equal to K, or excuse me, U hat is going to be equal to T with an underline multiplied by U. Okay. Right. Right. So the system that we seek, or kind of our goal, is to have like F is equal to something multiplied by U, right? And this something right here is going to be our element stiffness matrix. Our element stiffness matrix in the global system, or in the stationary. Okay. All right. And so we're almost there. And so you can see here that we have F and we have U right here. Okay. And so we're going to pre-multiply both sides by T inverse. And so if we, multiply this entire thing by T inverse just like that, okay, this is going to cancel out on that side of the equation. And so on one side we have just F. Okay. And on the other side of the equation we have T inverse multiplied by K multiplied by T. Okay. The nice thing about our transformation matrix T right here is that it has a special structure. And so if you take the inverse of T, it's actually the same thing as T transpose. Okay. And so if we replace that, so we have T transpose multiplied by K multiplied by T multiplied by U. Okay. This quantity right here, this is what we're looking for. And so this quantity right here in the middle, this is our element stiffness matrix in our stationary coordinates. Okay. Okay. And so our K, okay, which is what we want. Okay. I'll spare you all the gory details of performing, matrix multiplication with a bajillion cosines and sines. And so the end result looks something like this. So we have AE over L, and so that stays constant in the end. Okay. Then we have cosine squared, cosine sine, minus cosine squared, minus cosine sine. Okay. Then it's symmetric, and so I'm going to go ahead and write this down here. Okay. Then we have sine squared. Yep.
Is there another way to describe stationary coordinates? Is that global?
Yeah, global. You'll see global used a lot because it's kind of like a coordinate system for kind of the entire problem for all the elements to kind of refer back to. Yeah. So I use stationary just because I use global for some other things in this class. But global and stationary, they kind of mean the same thing for this. Yeah. And so this is our new element stiffness matrix for a 2D truss element. Okay. All right. And so it's a lot, and it took quite a bit to get here. Unfortunately, these problems can get a bit tedious because you can see here that now that we have a 4x4 system, the amount of variables that we have to compute here goes up pretty large. And so instead of having to compute just four element stiffness entries, now we have 16 to compute. Okay, but there is some solace. Okay. And so one thing I'll and you might have picked up on it when I was writing this down, that this element stiffness matrix is perfectly symmetric, okay? And so what I've circled here in blue is the same on one side of the diagonal as the other one. And so what you can do is you can just focus on just the top side of this matrix, okay? And so you just compute these quantities right here, right? And that's just how many? 1, 2, 3, 4, 5, 6. And so that's just 10 entries, okay? Still kind of a lot. And then you just reflect that across the main diagonal of the matrix. Okay? And so that might save you some work, but it's still going to be a little bit tedious. Okay. So any questions on this before we work it into an example? Okay. All right. So let's do an example just to kind of show you how it's computed. Just because we kind of spent a lot of time with matrices and trigonometry and everything. Okay. All right, and so let's consider just a single bar element or a single truss element. Okay. And let's assume that it's rotated 30 degrees relative to the horizontal. Okay. And so let's compute the element stiffness matrix. Okay. All right. And so, visually looks something like this. And so we have an element just like that. Okay. And this angle here is 30 degrees. Okay. In addition to that, we have the material properties of the element. And so the area is 2-inch square. The length we'll assume is 60 inches. Okay. And then Young's modulus we'll assume is 30 times 10 to the 6th psi. Okay. All right. So the way I like to do these, because it's a lot of plugging in, and it's kind of easy to kind of lose track if you're not organized. Is first thing I like to do is once I know the angle of the element, I compute what the sine and cosine of that angle is, and I just write it down. Okay. All right, so first let's start with cosine. Okay. So cosine is going to be cosine of 30 degrees. Okay. So cosine of 30 degrees is √3/2. Okay. Next, we have sine, and so sine of 30 degrees is 1/2. Okay. Okay. And so now that we know the material properties, now that we know sine and cosine, we can go ahead and plug this into the expression above. Okay. Okay. And so we have K is equal to AE over L, and so we have 2-inch square times 30 times 10 to the 6 psi divided by L. L here is 60 inches. Okay. And we're going to multiply this by everything up here. Okay. All right. So first thing we have is cosine squared. And so cosine squared is √3/2 squared. Okay. Next, we have cosine times sine. And so we have √3/2 times 1/2. Okay. I know what you're thinking. No, there is no easier way to do this. You have to plug in everything. Next, we have minus cosine squared. So we have minus √3/2 squared. Okay. And we have a minus cosine sine. So we have minus √3/2 multiplied by 1/2. Okay. Okay. And so that's the first row. Second row, we have sine squared. And so sine squared here is going to be 1/2 squared. Okay. Next, we have a minus cosine sine. So we have minus √3/2 multiplied by 1/2. Okay. And we have a minus sine squared. So we have minus 1/2 squared. Okay. And I'm using the technique that I used up there. So I'm just computing things on the upper half of the upper half of the matrix. And then once I've done computing those, I'm just going to reflect them across. Okay. All right, next we have cosine square. And so cosine square is √3/2 squared times cosine sine. And so we have √3/2 multiplied by 1/2. Okay. And then finally, in the bottom right, we have sine square. And so we have this 1/2 squared. Okay. Okay. All right, and so we can go ahead and evaluate all these things and then plug it all in, okay? And if you do that, then you get a 10⁶ out in front, okay? We have √3/2 squared, which is going to be 3/4, okay? Then we have a √3/4, okay? Then we have a -3/4 and a minus √3/4. I'm going to go ahead and reflect this down. And so kind of the easy way to write a symmetric matrix is to, write the first row first, and then I take that first row and I write it into the first column. And so, now that I've written the first row, I can write this as √3/4, then -3/4, then -√3/4. Okay. Next row is 1/4, -√3/4, -1/4. Okay. Okay. And I wrote that into the second column. Next, we have 3/4, √3/4, √3/4, and finally we have 1/4. Okay. Okay. And there is our element stiffness matrix for this example. Okay. Okay. Any questions on this? Yeah.
Probably set up the matrix for show the cosine, sine, cosine squares.
Yeah.
That one came from where?
Oh, yeah. So all the cosines and sine squareds here, they came from these transformation matrices. And so basically the structure or this matrix was formed by taking this matrix, which is basically a transformation from the local coordinates to the stationary ones. So we have cosine sine, minus sine cosine 0, 0, 0, 0, 0, 0, 0, 0. Okay. And then cosine sine minus sine cosine. Okay. We're multiplying this by our element stiffness matrix, which was AE/L. And then 1, 0, -1, 0, 0, 0, 0, 0. -1, 0, 1, 0, 0, 0, 0, 0. And then we have another one of these on the right side. So we have cosine sine 0, 0, minus sine cosine 0, 0, 0, 0, cosine sine 0, 0, minus sine cosine. Yeah, so all the cosine signs are basically a result of this kind of nasty kind of matrix multiplication right here.
And then those vary depending on how many elements we have.
So this is just for one element, and so for every element, you'll probably will do it on Monday, but when you have multiple elements, you have to do this for every single element that you have. So and then bring it all together. Yeah, it's tedious. I know this is not my favorite part of the class, and believe it or not, it actually gets worse later on. So this is just trusses, and so when we get to frames, it'll be a 6x6 element stiffness matrix. And if you have like 5 frame elements in your problem, you have to do 6x6 5 times. And so but that's on purpose. And so, I make you suffer through hand calculations so that when we actually get to the MATLAB, you'll be like, this is really nice because MATLAB's doing it for me. Yeah. I don't know how many anime fans there are here, but there's a famous series called Haruhi, where they had a section of the anime which is really, really bad. But it was all set up for a movie later on. So the badness of that part actually made the movie that much better. And so I see this as kind of the same thing. So the hand calculations are really bad, but it makes the MATLAB part just so much better. So it's like, wow, that's really nice that I don't have to do all this stuff. Okay. So any other questions on this? Okay. All right. So I don't think we have time to do the example today because we have just about 10 minutes left. And so let me talk about stress. Okay. We actually still have quite a bit to go. Okay, that's fine. All right. And so let's talk about how we compute stress computing stress in a truss bar. Okay. All right. So remember, what we started out today with, that, in finite elements, a lot of times we're not just interested in the primary solution, right? So we're not just interested in displacement. We're interested in what other kinds of derived quantities we can take from the solution as well. Okay. And one of those derived solutions in structural finite elements is the stress. Okay. So stress is really important because when you compute the stress in a structural element, that'll tell you a lot of times whether the element is going to fail or not. Because especially if you assume that the element is governed by linear elasticity. Okay. And so a lot of times computing stress has a lot of practical significance. Okay. And in fact, it was one of the quantities that I asked you to solve for in the ANSYS activity. Okay. And so the way we compute stress in a truss bar is actually fairly straightforward, okay? Because we know the definition for stress is just a force over the area, okay? And so we can compute the force, and so the force is nothing more than just the local, the local force that's down the length of the element, okay? Divided by A. Okay. And you can use either force, and so you can either use F1x hat or F2x hat. They're all the same, and so they both kind of do the same thing. Right? Okay, and so in order to compute the stress, according to this equation, all we need to do is compute the nodal force in the local coordinates. Okay. Okay. All right. And so let's go ahead and compute that. Okay. And so from our element stiffness matrix, okay, the local version, okay, we know, and I'm just going to do F2 hat. Okay. So we know F2 hat is equal to AE over L multiplied by -1 times U hat. Okay. Where U hat is both, has both the both nodes, so both node 1 and node 2. Okay. All right. So just like I did with the element stiffness matrix, we're going to augment this to include the y components, even though they're just zeros for now. Okay. And so we're going to have -1, 0, 1, 0. Okay. Okay. Right. And so that's where those zeros came from. And then now the next thing we're going to do is we're going to take U hat here and transform it using our transformation matrix. Okay. Okay. And so in other words, what we have is F2x hat is equal to AE over L multiplied by -1, 0, 1, 0. Okay. Multiplied by T underline times U. Okay. right? Where this U, this is our displacement solution in the stationary coordinates. Okay. Right, and so that's, so after we solve our finite element problem, that's something that we're going to have. Okay. Right, and so all we have to do here is we just have to take our T and we're going to multiply it through to this matrix right here. Okay. And so we have F2 x hat is equal to AE divided by L. And if we multiply that through, thankfully this is a lot simpler. So we have minus C, minus cosine, minus sine, cosine, and sine. Okay. Multiplied by U, our stationary U. Okay. Right. And then to get stress, the only thing we have to do is we have to take our F2 x hat and divide it by area. Okay. So we have stress is equal to F2 x hat divided by area. Okay. And so if we divide this by area, we can see here that the area here is going to cancel out. And so we have E over L multiplied by minus cosine, minus sine, cosine, sine, okay, times we have our U stationary. All right. All right, and so this equation gives us the stress in a truss element. Okay. And so you can use our direct stiffness results to compute the stress in that truss bar. Okay. Any questions on this? Okay. All right. And so we're just about out of time today, but I did want to kind of tease you on where we're going to go next, in case you wanted to start the homework. Okay. And so the next step is basically kind of put all this together. And so now that we know how to derive the element stiffness matrix in a 2D truss, now it's time to kind of put it together with a bunch of other elements. Okay. Okay. Right. And so, let's say that we have a system that looks like this. And so let's say we have 3 truss bars. Okay. Okay. And so we have a truss bar A, truss bar B, truss bar C. Okay. This angle here is 45 degrees. This angle here is 45 degrees. Okay. We'll say that this is fixed to the wall. Okay. This is fixed to the wall. This is fixed to the wall. Okay. And let's say that we know all the properties. And so we know the Young's modulus, we know the areas, we know the lengths and all that good stuff. Okay. And so to solve this problem, we actually just use the exact same process that we've done before. And so remember, our process is, number 1, element stiffness matrices. 2 is assembly. 3, boundary conditions. And 4 is solve. Okay. And 5, we actually have a new 5th step that we learned today that is optional in some cases, but sometimes you're interested in it, is derived quantities. Okay, so these will be things like stress, reaction forces, etc. Okay. But strictly speaking, you're actually done with the finite element problem after solving. Okay. And so the biggest thing that complicates 2D problems is this step right here. Okay. Now, when you compute the element stiffness matrices, it's much bigger of an ordeal because it requires a lot of computation. Okay. And so for this homework, and so, if you want to get started with the homework and to do the 2D problems, you actually have everything you need. So I actually gave you everything already. It's just that we haven't seen any examples in class yet. And so if you want to wait for the examples, you can wait till next week. But again, this homework is pretty long. And so I would definitely try to start it sooner rather than later. Okay? And if you want to use like computer programs like Excel or MATLAB to compute your element stiffness matrices, I'm totally fine with that. And so, I know I can be tough, but I'm not cruel, or at least I like to think that I'm not. And so, I don't want you sitting there like manually punching into your calculator cosine times cosine times cosine, And so if you want to use technology to simplify that for you, I'd say by all means, go ahead. All right, any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for this week. So thank you everyone for tuning in today. And so, again, definitely get started with the homework. I usually don't get this much warning for homeworks, but this is an exception. So, this is an unusually long homework assignment even for me. All right, so thank you for coming today. Hope you guys enjoy the rest of your evening, and I will see you next week.
So the CS always system we solved today, that is mixing off of the U being between the I and J.
Yeah.
Positive.
Yeah.
Quadrant. So if that changes, then it'll change.
Yeah.
Okay.
Question about the symmetric.
Yeah. So the way I like to think about it is that this is the main diagonal here.
Yeah.
And so things get reflected based on that. So when I'm done writing this first row, these three entries, they are the same as these three entries. And so symmetric all means that the rows is also the same as the column.
Right.
So you write out this first row, and this is like your pivot. So I like to think of it as you kind of rotate.
Right.
So this one becomes here, this one goes here. Same thing for the same thing.
Okay, perfect.
Yep.
So, for local, something called global coordinate system, so the local is used to make the stiffness matrix.
Exactly, yes.
And then you transform that matrix into the global coordinate system, then you solve the problem, and then it gets transformed back to the local.
So we only transform back to the local when we want to compute things like stresses. But the reason we transform it to the global system is because of assembly right here. Because it doesn't make sense if you have one element going this way and one element going that way. And if you compute the element stiffness matrices, each of their local coordinates, you can't combine them because like this, the x direction for this is different from the x direction for that one. And so you move them all into the same coordinate system so they all can be added together.
Got it. Okay, thank you.
Yep.
Question? Okay. Thanks, everybody.